Hi everyone, this is the second example of chapter 5.4. It is the question 96. So first, let's read the question. Question 96. A concave mirror of radius of curvature of 10 cm is placed 30 cm from a thin converging lens of focal length of 15 cm. Find the location and magnification of the image of a small light bulb sitting 50 cm from the lens. So the diagram looks like this. We have our light bulb represented by an arrow over here. It is 50 cm or 0.5 meter from the converging lens. And the converging lens and the spherical mirror has a distance of 0.3 meter between them. Now, every time we deal with two optical devices, or even three, what happened here is the image from the first optical device become the object of the second optical device. But we have to be careful here, and when we get there I will show you why. But the main idea is the distance of the image from the first optical device is not exactly the same as the distance of the object from the second optical device. We need to take the distance between them into account. We will do that in a couple of steps. So firstly, the first thing we should do is write down all the information. We were given in the question that the radius of curvature of the spherical mirror was 10 centimeter. So that means the focal point of the spherical mirror, I'm going to call it FM, so focal point with a subscript M for the mirror, is R divided by 2, so it's 0.05 meter in this case. We are also given the focal length of the lens, and I'm going to use F with a subscript of capital L, and it's equal to 15 centimeter or 0.15 meter. All right, so the first step, once we have all our data here, is to find the distance of the image. This distance over here. And again, we use the distance formula, so DO1. Now, by the way, I'm gonna use a different subscript for the first optical device and the second one. I'm gonna use DO1 to represent the object of the first optical device. I'm gonna use DO2 for the object of the second optical device. And same logic with the image here. So for the distance, we have 1 divided by DO1 plus 1 divided by DI1 is equal to 1 divided by FL, so the focal point of the lens here. All right, so if we input all the value that we have, we get a distance of the image of 0.214 meter. So this is the distance over here. But just like I mentioned, this is not the distance of the object. We need to take 0.3 minus the distance of the first image to get the distance of our object. So that's exactly what we're going to do. And we get 0.086 meter or 8.6 centimeter. All right, so that's our first step. Take a moment to write down these information. I need to erase everything to get to the second part of this problem here. All right, so now for the second part, we simply repeat this step. We now have the distance of the second object. It's 8.6 centimeter. We again use the distance formula. So the object, DO2 plus 1 divided by DI2 is equal to 1 divided by FM in this case. We are looking again for the distance of the image here. So let's just plug in the value that we have. And we get the value for the distance of the image to be 0.12 once we isolate this variable over here. So it's 0.12 meter or 12 centimeter in this case. All right, so that's the first part. We are also asked to find the magnification of the image. And when we deal with the magnification of an image that is magnified by more than one optical device, we need to multiply their individual magnification. I'm going to use the uppercase letter M to represent that combined magnification. It's equal to M1 multiplied by M2. So magnification of the first object, magnification of the second optical device, and we combine both of them. Now note, in both of these formula, there's a minus and they will cancel out. So we get DI1 multiplied by DI2 divided by DO1 multiplied by DO2. Now it's not to say that this term cannot be negative, but it is the negative on both formula cancel out. All right, so it's simplified in that format. Once we input all the value, we get a magnification of 0.6. All right, so that's it for question 96. We are going to be solving a lot more of these type of problems as they are challenging and they are a good way to put everything together. All right, see you soon.